Hi, my name is Beth, and I want to tell you about my favorite episode of Threshold. It's episode 2 in season 4, This Most Excellent Canopy. The tagline is a lyrical ode to the Earth's atmosphere, and that it truly is.
My name is Eva Kalea, and I'm Threshold's head of brand and culture. This Most Excellent Canopy is one of my favorite episodes of Threshold because it's just so lovely and beautiful to listen to.
Hi, this is Deneen, Executive Director at Threshold. I return to this episode again and again. It never fails with every listen to captivate me and move me emotionally, sometimes to tears.
I have to say, I'm embarrassed that I never thought about the atmosphere before this, about what it's made of, how it works, how improbable it is that it exists, and therefore that we exist.
As a longtime communicator on climate change and air quality, I learned so much and I was so inspired and just really made an impression from the very first sentence, talking about something I remember very vividly from my childhood, winning a goldfish in a plastic bag from a carnival, and being so happy taking it home, and realizing that we are also all goldfish swimming around in the atmosphere of the Earth.
The entire episode, from beginning to end, powerfully captures the beauty and the wonder and the science of this incredible thing, our atmosphere.
I think that this episode just asks of us to sit back and appreciate the atmosphere and all of the other invisible, underappreciated things in the natural world.
I hope everyone gets an opportunity to listen to this to understand more about the atmosphere we all breathe in every day that allows us to form every word and sing every song and supports our life and all life on this planet.
Threshold is made with the support of listeners like you. Join us at thresholdpodcast.org.
When I was a kid, you could win a goldfish in a bag at the carnival. Is that still a thing? These traveling fairs would come through every summer and set up rides like the Tilt-A-Whirl and the Silly Silo in the middle of our little town. We'd all go and buy tickets, ride the rides, and play games, like throwing rings over bottles or whatever. And if you won, one of the prizes you could get was a goldfish in a plastic bag. As I've been working on this season of Threshold, I keep thinking about those goldfish, about how I am one. We all are, swimming around in a bubble of life-giving air that we call the atmosphere. It's a warm cushion protecting us from the frozen barrenness of space, and most of the gases that make up that cushion are in the first 10 miles. If we could defy gravity and walk straight up away from the surface of the Earth, we'd cross the bulk of the atmosphere in a couple of hours. And beyond that thin membrane lies death. Cold, dark emptiness. Our relationship with the atmosphere might be more intimate than our relationship with anything else on the planet. And maybe that's why it's so hard to appreciate it. Just like the goldfish, it's the water we're swimming in. But unlike the goldfish, we have the capacity to understand our atmosphere. And I think this is a part of the quest to limit global heating to 1.5 degrees that often gets skipped. The atmosphere is the central character in the climate drama, but most of us have no idea what it really is or how it works, how powerful the atmosphere is, and how fragile. So let's fix that. Let's spend an episode getting better acquainted with our little cocoon of air. I've recruited 3 guides for us.
My name is Francina Dominguez.
I'm Hannah Wakeford.
My name is Anjali Tripathi.
Francina Dominguez is an atmospheric scientist, Hannah Wakeford and Anjali Tripathi are astrophysicists, and they're going to help us explore the mystery and wonder of our most excellent canopy, the atmosphere.
It's like underappreciated transparency.
Our atmosphere is like a reservoir for life to flourish off of.
We cannot negotiate with nature. We cannot negotiate with the planet.
This planet will survive. It will reset itself. It will turn into a different atmosphere. But we're not designed for that. And evolution is a lot slower than we'd like it to be.
The atmosphere is mysterious, almost by definition. It's the word we use to describe something vague, lying in the background. The atmosphere in the room, the atmosphere of the occasion. It's a mood, an undertone, an invisible, certain something. We can't put a sign up in front of the atmosphere and go visit it like a national park. We can't stand on its shores and witness the damage we're doing to it, like on a beach after an oil spill. And I think that's partly why we've been so slow to react to the climate crisis. I mean, it's hard enough to get people to care about protecting a beautiful mountain range or a charismatic wild animal. In this case, we need to get deeply invested in the fate of something that's almost the definition of intangible. We spend our whole lives inside it, rarely thinking about it, but pluck us out of our atmosphere, and we are as helpless and gasping as a fish pulled out of a lake.
The first thing is just how beautiful it is, right?
Francina Dominguez is a professor in atmospheric sciences at the University of Illinois at Urbana-Champaign.
If you sit down and look at a huge storm or even fair weather clouds, the way that they move and morph is just gorgeous.
And that beautiful movement has all kinds of really important purposes.
Our atmosphere is responsible for everything.
Hannah Wakeford is an astrophysicist based at the University of Bristol in the UK, and she says it's almost impossible to overstate the importance of the Earth's atmosphere.
It is responsible for the water cycle. It is responsible for the recycling of carbon dioxide, and it's responsible for waves on the ocean and the circulation of Saharan dust around the planet. It transports biological material. It pollinates plants. The wind structure on our planet creates biomes at different latitudes, which allow us to grow very different kinds of crops.
The atmosphere flows around the planet in the form of wind and clouds and storms, transporting water and warmth from place to place.
It's carrying essential ingredients that make this mind-boggling complexity of organisms possible.
So if you were going to try to compare the atmosphere to something else on the planet, what would that be? Is there anything else that's kind of like the atmosphere?
The atmosphere? No, it's so unique. It's like underappreciated transparency. I think this underappreciated magical substance.
There's just these really small things, these little nuances that the more you look, the more you go, wow, how did I not know about this? How does this all fit together? It's so infinitely complex.
And also so simple. As simple as breathing. We take atmosphere into our bodies. Every inhalation and exhalation we make is an interaction with it. It fills our lungs, gets dissolved into our blood, and races to our hearts, where it's then pumped out to feed our cells with the oxygen they need to move our muscles, fight off disease, digest our food, generate thoughts. Every piece of art we've ever made, every structure we've ever built, every song we've ever sung, every word we have ever uttered has been a collaboration with the atmosphere. We can live for a little while without water. We can live even longer without food. But when we lose our ability to take in the atmosphere, when that collaborative dance between us and the air breaks down, we die almost instantly.
Our atmosphere is like a reservoir for life to flourish off of, and that reservoir dictates a lot of what happens on the planet.
Astrophysicist Anjali Tripathi is affiliated with the Harvard-Smithsonian Center for Astrophysics.
I would encourage you to lie back on the grass and stare up at the sky, take a deep breath, and look at the clouds passing by, because that ability and that opportunity is, I would argue, underappreciated in our daily lives. Even if we go and move off to another nearby planet, we're going to have to do a lot of work to make that atmosphere into something that we can work with in the same way. Sci-fi literature is rife with options of what you could do in those situations. None of them are, take spaceship to planet X, get out, enjoy life, done. It's not that simple.
And we don't only need the atmosphere to breathe, we also need it for protection.
Space is a pretty hostile place.
For one thing, it's really, really cold. Baseline space temperatures are around negative 455 degrees Fahrenheit, or negative 270 degrees Celsius. So cold. And even though we can't see it, there's a lot of stuff flying around up there that can hurt us. Stars exploding in faraway galaxies send charged particles hurtling through space, and those particles can damage our cells. Our own star, the sun, produces some unfriendly particles as well. Anjali says that's one of the reasons she thinks of the cushion of air around our planet as a safety blanket.
It's also a safety blanket because it takes the heat, quite literally, for us when we have impacts.
All kinds of space debris burns up in our atmosphere before it hits the ground, saving us from having a surface dominated by craters, the way the moon and Mars are. But what is that safety blanket actually made of? What is an atmosphere?
An atmosphere is a collection of gases that are bound by gravity to a planet.
They're held by the gravitational pull because they have mass. And it is counterintuitive that we are basically underneath this ocean of air. I'm appropriating this from the book, An Ocean of Air by Gabrielle Walker. So it's a beautiful book. At the beginning, it talks about this, that it's a non-intuitive concept that the air has weight, and it actually has a ton of weight.
Just like when a scuba diver goes underwater and can feel the weight of that water pressing harder as they go deeper, we're in an ocean of air. Even though we can't see the atmosphere the way we can see the water in the ocean, it's still a substance that can be set on a scale and weighed. It's about 300 miles thick from top to bottom, but the bulk of it is in the first 10 miles closest to Earth.
It took humanity thousands of years to figure out that air had mass. It's completely non-intuitive. And then imagine then afterwards trying to understand that air was made of different ingredients, right? It's not intuitive at all.
But not every planetary body has an atmosphere. For instance, the moon basically has none. So how did our atmosphere come to be?
So the Earth is thought to have always had some kind of atmosphere, but we are either on our second or third or fourth atmosphere, depending on which combination of things you would say defines a break in what kind of atmosphere you have.
About 4.5 billion years ago, when the Earth was born, our atmosphere was mostly helium and hydrogen.
So when we first formed as a planet, we would have been very hot. It would have been a kind of molten lava world. And then we actually went through a cataclysmic event when the moon formed. This would have disrupted the atmosphere completely, and it would have reformed. But our secondary atmosphere came when volcanoes let off gas. So the early Earth was highly volcanic, highly active world. And then over time, something happened. And about 2.2 billion years ago, the CO2 dropped and the oxygen, O2, arose. It's called the Great Oxygenation Event, where oxygen kind of came about in our atmosphere as the second most dominant component.
And this was a huge shifting point in the Earth's history.
It started with cyanobacteria, some of the first organisms on our planet that were able to photosynthesize, which meant they were essentially exhaling oxygen.
So they're in the ocean, and the oxygen is starting to accumulate in the ocean water and in the rocks. And little by little, this oxygen starts to trickle into the atmosphere. Okay, but this is very slow, right? Billion years, this is in the making. Slowly but surely, you're having this trickling of oxygen into the atmosphere. And about 600 million years ago, we hit this threshold, which is about 5% oxygen. And this just is kind of like a burst of life, where you now can have multicellular organisms. Now you have organisms with eyes and teeth and that can move. So it's this kind of threshold in the amount of oxygen that enables complex life to form.
Wow, so it took a long time between beginning to release oxygen into the air and getting to complex life, like a really long time.
Yes, a really long time. A really long time. Yeah.
So the Earth's atmosphere allowed very simple life forms to emerge, and then those life forms themselves actually changed the chemistry of the canopy of air around the planet, adding more and more oxygen bit by tiny bit, which allowed more and more complex life forms to evolve.
So there's so many changes. There's an evolution of a planet through time, and you can see that imprinted in the planet's atmosphere.
Today, our atmosphere is about 78% nitrogen and 21% oxygen.
And then that only leaves about 1% left for everything else.
Most of that 1% is argon,
which is this element that we actually only discovered by taking some air, pulling everything we knew out of it and said, oh, what's this leftover piece? Oh, okay, I guess we'll call that argon. And then, at tiny fractions, maybe 0.04%, we have carbon dioxide and other gases in the atmosphere. So when you think about the atmosphere, really we're saying this nitrogen, oxygen, argon bath that is a veneer around our planet.
Did you catch that? Carbon dioxide, the planet-warming gas that's causing so much trouble for us these days, is just a tiny fraction of the total atmospheric brew.
That percentage is somewhere around 0.041 at the moment.
It's so small compared to 78% nitrogen.
It's so small.
So I'm guessing you might be wondering what I was wondering at this point. If carbon dioxide is such a teeny tiny portion of the atmosphere, how can it be so important? We'll find out after the break.
If you're enjoying this episode of Threshold, you can take your love to the next level with some stylish Threshold merch. Check out our shop for some thoughtfully curated goods, including organic cotton tees, hoodies, caps, handcrafted ceramic mugs, and tote bags featuring art from Sally Dang. We have a special sale going on this month to celebrate the Earth, so head on over to thresholdpodcast.org/shop or click the link in our show notes. Your purchases help fund our nonprofit journalism, so go to thresholdpodcast.org and hit the shop button. Thanks for your support.
I'm Austin Amestoy, host of The Big Why, where we answer your questions, large or small, about Montana. Find out what happens when you recycle in Montana, why salmon never made it to the Clark Fork River, who owns the most water rights, even why so many people report seeing UFOs in Big Sky Country. And you can ask your own questions right now. Find us at bigwhy.org or wherever you listen to podcasts.
Here's another podcast we think you might enjoy. The Carbon Copy is a weekly news analysis show about the business and tech trends shaping climate solutions. Host Stephen Lacey is a veteran climate and energy business reporter who brings deep historical knowledge of how energy systems work and how climate change connects to everything around us. Each week, he digs into the business and technology stories that explain the rise of clean energy, the challenge to fossil fuels, and how the energy system is transforming in dramatic ways. From America's historic climate bill to record-breaking wind and solar projects to the war over gas stoves, the Carbon Copy is telling the most compelling stories about how the solutions will play out. Listen to the Carbon Copy on your favorite podcast app.
Welcome back to Threshold. I'm Amy Martin, and before the break, we were talking about how carbon dioxide makes up just a tiny percentage of our overall atmosphere, less than 1%. So how is it possible that having less than 1% of anything in the air could be such a big deal? Atmospheric scientist Francina Dominguez says one way to start to wrap our heads around that is to imagine our planet without any atmosphere.
The Earth would be a ball of ice.
She says if we had no atmosphere at all, the Earth's average temperature would be negative 18 degrees Celsius. That's a little below 0 Fahrenheit, so way below freezing. But
in reality, we're at about 15 Celsius.
That's around 60 degrees Fahrenheit.
That's our average temperature. So it's a huge difference, right? Between frigid conditions that could not sustain life to balmy, not too hot, not too cold conditions that enable these spectacular life forms.
And that difference between a completely frozen Earth and the much warmer Earth we actually have is the greenhouse effect, the special way that carbon dioxide and a few other trace gases trap the heat around our planet. I'm guessing most of us never heard about the greenhouse effect until we started hearing that it was a problem. But actually, we need a certain amount of greenhouse gases, like water vapor and CO2 in our atmosphere. So the greenhouse effect in and of itself is not a bad thing, but it is a delicate thing. So how does it work, really? We all know carbon dioxide is classified as a greenhouse gas, but how does it trap heat around the planet, while much more abundant gases like nitrogen and oxygen don't? I asked Francina to explain it to me, not at the PhD in atmospheric sciences level, but just with the goal of understanding the basics of the greenhouse effect well enough that I could explain it to someone else, without Googling anything. And she started with radiation.
All objects emit radiation, and the wavelength depends on the temperature of the object. So the sun, which is super hot, emits primarily in the short wave. But the Earth, which is much cooler than the sun, emits primarily in the long wave.
So the energy flowing into the Earth's atmosphere from the sun comes mostly as shortwave radiation, and then the Earth bounces some of that energy back out into space, mostly as long-wave radiation. Francina says it's this slower, cooler radiation emitted by the planet itself that really matters when it comes to the greenhouse effect, because that long-wave radiation behaves differently when it meets different gases in our atmosphere. When it meets oxygen and nitrogen, it just keeps on going. But when long-wave radiation meets up with carbon dioxide and water vapor, something different happens.
So what sets water vapor and CO2 apart from, say, nitrogen and oxygen, which is what, again, most of our atmosphere is made of, is that they're kind of lopsided. They're not completely symmetrical, and they essentially jiggle.
Because of how these molecules are shaped, they move differently than nitrogen or oxygen. They're much more creative dancers. And that causes them to block some of the long-wave radiation flowing up and away from the planet. You could think of these lopsided, jiggling molecules of CO2 and water vapor as molecular speed bumps, or maybe sponges.
When the radiation hits them, it gets absorbed, and that air is going to heat up, essentially, because it's absorbing this radiation.
That warmth then radiates back down toward the surface, and the whole system gets a little hotter. The land, the water, the air. So that's the greenhouse effect in a nutshell. Dancing, asymmetrical molecules absorbing long-wave radiation from the Earth.
It's like a blanket. They're forming this blanket over us that's kind of keeping our heat from escaping because it's being kind of re-radiated back to us.
And at the same time that this blanket is preventing some of our long-wave radiation from escaping, which helps to keep us warm, it's also blocking some of the very highest intensity radiation from the sun, which would be deadly for living things if it made it down to the surface of the planet. So the atmosphere is doing all kinds of things for us all at once.
So at the longest wavelengths, the atmosphere keeps us warm and does not allow all of that energy just to be lost to space. So think of it as a blanket. But at the highest, at the very high energy wavelengths, the atmosphere is a shield because it protects us from this shortwave high energy radiation. So a shield and a blanket.
It's like a magic blanket.
It's like a magic blanket, yes. So yeah.
And again, the part of that blanket that's doing the most to keep us warm is the smallest part, the less than 0.5% of the atmosphere that's made up of carbon dioxide and other trace gases. These lopsided CO2 molecules interact so powerfully with the Earth's long-wave radiation that adding just a few more of them can radically change the climate. They're like salt in the atmospheric soup, a tiny proportion of the whole with a huge effect.
Trace amounts of these gases make the difference between a snowball Earth and the Earth that we currently have. So very small amounts make a huge difference.
The greenhouse effect is a natural process of our atmosphere. We didn't create it, but we can mess it up. By treating the atmosphere like a sewer, as a place where we can just thoughtlessly dump heat-trapping gases, we're running a very dangerous chemistry experiment.
I guess we cannot say it any clearer in the sense that we know we're modifying the atmosphere in a way that's detrimental for all living species. We've known this for decades. It's a matter of us realizing that if we continue on this path, the consequences are going to be just mind-boggling.
The thing with the Earth's climate is there's these things called feedback loops.
Hannah Wakeford.
And there's not just one feedback. It's not just about having greenhouse gases in your atmosphere. It's about how much ice have you got? How much light is being reflected? How many clouds are you making? So it's all about how these different processes and these feedback loops interact with each other.
To take just one example of that, if you listened to season 2 of our show, you already know that our CO2 emissions are helping to thaw out frozen soil called permafrost. And then that soil releases more greenhouse gases as it warms up, which leads to more warming, which leads to more permafrost thaw, etc. The extra carbon dioxide that we're adding to the air is kind of like kindling that can ignite these much bigger fires in other parts of the Earth's interconnected systems.
And if we hit a tipping point on any one of those, it can send other ones into a spiral where they can't counter it anymore. And that's the biggest problem with CO2. It is adding to a feedback mechanism that we can't counter.
And if we want to see atmospheric feedbacks that make life next to impossible, we don't have to look very far.
We can look to Venus. It is not nice to be on the surface of Venus.
The atmosphere of Venus is incredibly heavy, almost 100 times heavier than Earth's.
It would literally be crushing you.
That's Anjali Tripathi again, and she says in addition to smashing you with its atmospheric pressure, Venus would burn you alive.
And so you can think about it as the same temperature as maybe a wood-fired brick oven for making pizza. That's what it would feel like to be on Venus. So lead would melt.
So why is the Venusian atmosphere so heavy and hot? Well, it's closer to the sun than the Earth, but that doesn't fully explain the difference. Scientists think that Venus likely experienced a runaway greenhouse effect. CO2 and water vapor trapped heat around the planet, and that heat led to the release of more greenhouse gases, and now the planet is uninhabitable, at least to any creatures that are anything like us.
Venus is about the same size in terms of radius and mass as the Earth. We're sometimes called twins, and Venus is the evil twin because it's such a horrible place to be.
The process of atmospheres forming and changing is super complex, and there are countless factors at play here. But still, it's worth noting that our nearest neighbor and our closest planetary twin ended up with a hellscape of an atmosphere because of a greenhouse effect gone haywire.
It just makes you stop and wonder and appreciate the fact that you've got everything finely tuned in a way that it's working for us, because it seems like it's so much harder for that to happen than not to.
Not only is the atmosphere working for us, we work the way we do because of the atmosphere. As just one example, take the way we see. There's all kinds of electromagnetic energy flying around us, gamma rays, infrared rays, radio waves, but we can only see a narrow band of that energy. That's the window that we call visible light. But why is that particular range of waves visible to us? The atmosphere. Francina Dominguez says what we call visible light is just the stuff that doesn't get filtered out by the air around us.
These are the wavelengths that our atmosphere lets pass, and our sensors have adapted to those exact wavelengths.
And if we'd evolved in a different sort of atmosphere, our eyes would work differently, and we'd call some other part of the spectrum visible. That's pretty mind-blowing to contemplate, really. This amorphous stuff that we rarely think about, the air, actually sculpted the shape and function of our bodies.
We see in these wavelengths that are transmitted through the atmosphere. So that's pretty cool.
We might want to keep this in mind as we dream about moving to a different planet someday. You can take us out of Earth's atmosphere, but you can't take Earth's atmosphere out of us. It made us who we are, and no matter where we go, this atmosphere is our true home. If we ever do try to make a life for ourselves on Mars or anywhere else, we'll have to spend a lot of time and money generating an atmosphere, using Earth as a blueprint. We truly will be like the goldfish in the baggies then, either walking around in spacesuits with portable atmospheres or living inside shelters that recreate what we have here. If that ever happens, I think people will look with longing and envy at the freedom we have now, walking around unencumbered in an atmosphere that works for us without giving it a second thought.
You know, our atmosphere will always be intrinsically special because it is our atmosphere.
Anjali Tripathi's area of expertise is actually atmospheres on planets outside of our solar system, called exoplanets. And she says so far, we haven't found any planets anywhere with atmospheres that match our own.
I don't like to say that everything we see here could not happen again anywhere else, because of course the laws of physics are the same elsewhere. But we keep looking and looking, and nothing looks the same. It's like people's faces, right? No two are the same. But it is also my hope that our atmosphere is not that special in terms of how common it is throughout the universe, because there should be these ingredients other places. Like, it shouldn't be, this is the one place in the universe where there was enough disorder to kick life into motion. Because again, life is actually something that needs to come out of a little bit of chaos. If there's too much order, probably not everything comes together in the right way. So it's my hope that other inhabitants of the universe can enjoy an atmosphere like our own, because we do find it to be pretty special.
Maybe some alien astrophysicists on a distant planet are looking through their telescopes at our atmosphere, wondering who we are or if we exist at all. Maybe they're going through the same kind of phase we are, a time of realization and reckoning with our impact on the atmosphere and the planet as a whole. Maybe this is a Rubicon all technologically advanced species cross, or don't.
This planet will survive. It will reset itself. It will turn into a different atmosphere. It will come up with a CO2-rich atmosphere with lots and lots of clouds all the way up. But we're not designed for that, and evolution is a lot slower than we'd like it to be.
If we are going to limit global heating to 1.5 degrees Celsius over pre-industrial temperatures, we need to get passionate about the atmosphere, to fall in love with it, just like we fall in love with forests and rivers and creatures down here on the surface of our planet.
The beauty and the complexity of the living organisms on Earth is made possible by this interaction of these three things, essentially. The sun, the atmosphere, and the earth interacting together to create all of this amazing beauty and complexity.
It's almost like the atmosphere serves as connective tissue between the sun and the earth. And although that tissue is extremely multifaceted and strong, it's also extremely sensitive. It's protecting us, so we need to protect it.
We can do this, and there's just no reason not to do it. We can't wait. We can start right now.
The climate crisis is teaching us that we have a power that we didn't ask for, and in many ways do not want. The power to fundamentally change the atmosphere, and therefore the future of life on the planet. That is a heavy burden to bear, but we can't turn back time or wish this power away. The choice before us is whether or not we'll take responsibility for it.
Part of what's making our atmosphere special is that we're here to appreciate it, but it's also special that we then have that ability to do something about it and shape its future.
Picture all of us Earthlings nestled in here together under this life-giving, climate-stabilizing, magical blanket, this most excellent canopy, this ocean of air that birthed us and made us who we are. Sometimes we talk about the need to save the planet, but I think we've got it backwards. If we manage to keep living and learning and evolving here, in the black and barren vastness of space, it'll be because our atmosphere continues to save us. In our next episode, we're taking a trip to the birthplace of the Industrial Revolution and the climate crisis.
So this whole idea of King Coal, you know, I mean, you absolutely can put that here. That's the legacy.
Travel with us to 18th century England next time on Threshold.
I'm Andy, calling from Madison, Wisconsin. Reporting for this season of Threshold was funded by the Park Foundation, the High Stakes Foundation, the Pleiades Foundation, Newsmatch, the Llewellyn Foundation, Montana Public Radio, and listeners. This work depends on people who believe in it and choose to support it. People like you. Join our community at thresholdpodcast.org.
This episode of Threshold was produced and reported by me, Amy Martin, with help from Todd Sikafus, Nick Mott, and Erica Janik. The music is by Todd Sikafus. The rest of the Threshold team includes Eva Kalea, Talia Farnsworth, Shola Lawal, Casey Simpson, and Anine Weisky. Thanks to Sarah Sneath, Sally Deng, Maggie Contreras, Hannah Carey, Dan Carreno, Luca Borghese, Julia Berry, Kara Cromwell, Katie DeFusco, Caroline Kurtz, and Gabby Piemonte. Special thanks to Ariana Verullo-Clark and Ulf Nilsson. An extra special thanks to listeners who sent in recordings of breath and wind and frogs and elephant seals used in this episode. Christopher McAllister, Anna Taher, Claudia Stryjak, Evan Levy, Jürgen Morgenstern, and Shelley Eisenrich. These are just some of the listeners who participated in our Audio Mosaic project. And actually, that project is still happening. If you'd like to submit a recording that might end up in this season of our show, go to thresholdpodcast.org and look for the button that says Audio Mosaic Project. Again, that's thresholdpodcast.org.